Hello, my name is Nikolai, and this is the short presentation on the work that we did with Neo4j on path indexing, and specifically developing path indexes, efficient path indexes in Neo4j graph database. This work was done by Joachim Kuipers under the supervision of myself, George Pletcher, and Tobias Lindecker. So what did we set out to do in this work? First of all, it is widely known that the core of contemporary graph query languages relies on navigation on paths. And specifically, often we would like to navigate on paths which are constrained in some way. So those could be shortest paths, this could be some other constraints, and one common constraint that is used is limitation on labels that can appear on the path. We already worked on efficient implementation of path indexes before, and in this work, the primary goal is to identify the use cases in which path indexes could be useful, and specifically in the context of industrial scale databases. So we're talking real queries, real graphs, and queries which are complex, and the graphs which are very large. What we discovered in this work is, of course, also applicable to implementations which are outside of Neo4j. In this work, we prove that such implementation is possible in the industrial grade system such as Neo4j. So here is some background, and this background relates to Neo4j and the definitions of path indexing that we were using in our work. So specifically, we were focusing on the property graph data model, which is indeed one of the most popular graph data models in use today, and it's fairly expressive. And we were focusing on a cipher query language. So what are paths for us, and specifically what are path patterns? So paths are defined as path patterns, and indeed the path pattern is just a string of alternating node and edge labels along the path. And we also specify, in addition to the labels, node and edge labels, we specify the direction of edges. So here's an example of a pattern in which we have a path, the path of length 2, so it consists of 2 edges. And the edges are, so we have incoming edge in B, and we have, again, incoming edge into node labeled with B, from node labeled with A over the edge X, and from node labeled C over the edge Y. Now, how do we define path indexes? So the path index is defined by a path pattern, so the path pattern that I just described. And essentially, the path index, it contains all the paths that are defined by this pattern, all the paths in a graph. And what we do is that we store such an index, so the key is going to be the pattern. We store such an index, and we implement such an index as a B+ tree in Neo4j database. So once we have the implementation of a path index, what did we need to do in order to start supporting such indexes inside Neo4j? So we needed to modify several components inside Neo4j. So first, so query and the query gets parsed, so this stays the same. But then we needed to modify the planner in such a way that it is aware that now we have this new index, which indexes paths, and we need to be able to choose from plans which contain index operations over these path indexes. So we needed to add that, and we added this. Then equally important, we needed to modify cost estimator in such a way that we needed to have a correct estimation of plans with path indexes, such that the planner would indeed choose the plans with such data structures. So we modified the cost of these. We then, of course, modified the runtime. So the runtime took into the account the execution over path indexes, and it was able to, so we essentially added operators that index scan operators inside Neo4j that utilize those indexes. And of course, the index itself that has to be stored and available in Neo4j system. And finally, what we needed to do is we studied the maintenance of such data structures, because of course, path indexes akin to materialized views, you need to think about efficient maintenance of such data structures. And for that, we needed to work on a transactional engine in Neo4j in order to support the maintenance of path indexes. For the evaluation, we used two syntactic data sets, the ones that we generated, and we used two real-world data sets, Yago and Geospecies. So this is the encyclopedic data set, and this one is the biological data sets. So here's the results on the experiments on the path index maintenance. So specifically in this experiment, we wanted to know how to choose and which sub-patterns could be useful in maintaining the overall path index pattern. And the results is that, okay, so some patterns indeed allow us to speed up the maintenance significantly on the different data sets, whether the data is correlated or not. But some others were actually not beneficial at all in the maintenance of path indexes. And this is due that if you have a specific pattern indexed, you're forced to choose a plan which will involve the index scan of this subpattern. And then if this subpattern is just not selective, then this plan would be subpar in not having this plan at all. So we can have potential drastically reducing the performance instead. We also, in addition to maintenance, we also studied the query evaluation using path indexes. And what we found out is that if you're smart about the pattern that you choose, you can get a great performance, which is afforded by path indexes, with reducing both intermediate result size and the query time. But this only happened when we used the correlated data. If we used the data without correlations, then it was actually quite difficult to choose a good index in order to speed up the query evaluation. And actually, we didn't get any performance gains on such a data, which also makes sense, as such indexes typically explore high correlations in underlying data. And of course, such high correlations exist coming back to real data. And we were able to, on real data, you can get a very significant gain by using path index on real data sets such as Yago, and actually at a very small cost as well. Path index can offer great advantages by actually being small because the pattern is selective, and also by preventing the high Gardner intermediate state. And in our future work that we're working on is that, okay, so how do we then use good path indexes? And what is the optimal set of path indexes to use given some real-world workloads and constraints?